Welcome everyone, good afternoon. Welcome for our online colloquium series. And today we have this concept of a pre-colloquium talk. Just to make sure it's not I don't think it's a prerequisite for next week's talk. So next week we will have a talk by Roland Schweicher. I see him here, right? And today we have a talk by Tobias from Saarland University, which is aimed for introducing the topic for students, I think. So everyone is encouraged to ask questions, and I think the goal of these events is to have a fruitful discussion, and people will learn some exposition to nice topics. Okay, so please go ahead, Tobias. Thank you for coming.
So thank you very much for the introduction, and of course, thank you very much for setting up this very nice event. I very much like the idea of this pre-colloquium talk, and I will try my best, to satisfy some of the expectations. So the question, which is is the title of my talk, is what actually is free probability theory? And I mean, it's somehow a biased introduction in the sense that well, I cannot cover all the interesting features of free probability theory, but at least I will try to highlight a few of the aspects which are related to what Roland is telling you in his colloquium talk next Monday, but not exclusively. I mean, I will really provide the background, and I will try to give you an impression what really free probability is about. Okay, so let me start with the following. So somehow the takeaway message right at the beginning. So the short answer to the question, what actually is free probability theory, is written in the first line here. The answer is free probability can be seen as non-commutative probability theory, where I should say it's the language of non-commutative probability theory, plus this very particular notion of a kind of independence, the free independence, which makes it very particular and special. So, I mean, what you should keep in mind is the fact that starting from classical probability theory, there are several ways to come up with non-commutative versions of probability theory, but they have a kind of classical flavor in the sense that they are built on top of the notion of classical independence, in a sense. Think, for instance, of Brownian motions, let's say on Lie groups or something like this. But we take this language and we add some very particular notion of freeness, which makes it very non-commutative, and which turns out to have connections to various other fields. But in order to make sense out of this takeaway message, I should maybe first tell you what actually do I mean by the language of non-commutative probability theory. And in order to make this, to give you an intuition about this, let me first recall what we mean, what the language of classical probability theory is. So let me start. Classical probability space. So this is the underlying setting of probability theory. So what is it? We typically start with a set, let's say omega, and on this Z we have a sigma algebra, sigma field F, and a probability measure defined on this. So as I said, we have just a set, the sigma field, and a probability measure. And well, this is the underlying setting, and then you start to define some important object, namely what is called the expectation. And this, of course, is nothing but E of x. So you take a random variable x, and what you are going to define is the integral over omega, and then you take x omega, where omega, little omega is just a variable with respect to which you integrate. So little omega is coming out of capital omega, of course, and then you integrate with respect to the probability measure. And well, there are several reasonable spaces on which you can define this. So for instance, you can do it in the particular setting of bounded random variables. Over your probability space. Okay, this is the very classical starting point of probability theory. And well, the intuition of, or the idea behind non-commutative probability theory is to make this concept non-commutative in a very well established way, established in the sense that this procedure somehow applies to many other concepts, classical concepts that are turned into a non-commutative counterpart. So for instance, if you're doing operator algebras, let's say C-star algebras, sometimes C-star algebras are considered as non-commutative topology. So why this? The procedure is you start with a compact Hausdorff space, topological Hausdorff space. You consider on this space the functions, complex valued functions, and then you consider the algebra of all these functions, and they form a C-star algebra. You axiomatize this object, and then you call this C-star algebra by just dropping the condition of commutativity. The same applies actually in some sense to von Neumann algebras, which are in the same spirit considered as a kind of non-commutative generalization of measure theory. And here we do the same. So we follow the strategy. Instead of working with the classical probability space, we pass to the non-commutative functions, we pass to the space of functions over the space, and then we try to imitate the structure. We have already done the first step. We pass to functions, a suitable class of functions, and these are the bounded L infinity functions. And then, in addition, as an additional structure which really implements the probability the probability measure, we have our expectation. So let's say we have a tuple L infinity of omega fp together with the expectation, and this somehow encodes a lot of information about the underlying non-commutative, about the underlying classical probability space. And following the same procedure that I explained before in the case of C-star algebras and von Neumann algebras, we just try to axiomatize what this kind of object is, what is really characteristic of this object. So we try to find conditions which allow you to replace this by a more general object. And well, this more general object is what I'm going to define now. Definition. So A non-commutative probability space A, phi. So you shouldn't be confused. It's not really the analog of the classical probability space. It's more the analog of the bounded measurable functions over this probability space. And this consists, by definition, of a unital complex algebra A, and the unit in A will be denoted like this. And on the other hand, we have a linear map, let's say phi, from A to the complex numbers. And the only requirement which we impose in addition to linearity is that phi maps the identity of our algebra to 1. This kind of normalization. And the way you should understand this is that the algebra consists, so the elements of this are non-commutative random variables, and the phi takes over the role of the expectation. So this is how we call it. We call this the expectation. On A. Okay. This is the general concept, and you see, I mean, the requirements are quite weak, but it still has the flavor of probability theory, as we are imitating the algebra of random variables plus the concept of an expectation. So let's give examples, and the examples, or maybe before, I should perhaps highlight this important concept. So some examples, actually two, I will start with two. The first one we have already seen, namely just the L infinity, so the measurable, bounded measurable functions over our probability space together with the expectation. So this is classical probability theory. But then we can also go slightly non-commutative, but less probabilistic in the sense, well, you just take the complex n by n matrices, so the n by n matrices with complex entries, and on this, you consider the normalized trace. So just to make it precise, so the normalized trace is just 1 over n. N is the dimension of the ordinary trace. And this simply means that, so if I take the normalized trace of a matrix, let's say little a, then this is just 1 over n times the sum of the diagonal elements of the matrix. So just the ordinary trace normalized by this additional factor 1 over n. And this, of course, is just in order to make the identity matrix having trace 1. So this, well, is definitely an example of a non-commutative probability space. It's maybe not clear why you should call it probability, because this is really deterministic, but still it fits into this framework. And then if you combine these two spaces in some sense, let's say by a kind of tensor product, then you will end up with what is called random matrices. We will come back to this in the sequel, but just to give you a feeling that there are much more examples which fit into this framework and which show that this is really a very general setting. Okay, so this is the setup, but then the question is, what can you do with this? And of course, probability theory starts with the setting of a classical probability space and builds up several notions. And one of the fundamental notions that you learn in classical probability theory are the notions of distributions. And this is also fundamental in non-commutative probability theory. So let me define this. So let me say the non-commutative distribution of, and for simplicity, we just take a finite tuple, and this is I'm going to denote by capital X. So as I said, it's going to be an n tuple of x1 up to xn, where each entry comes from our underlying non-commutative probability space, and the non-commutative distribution of this n tuple is just the following map. It's defined on the algebra of non-commutative polynomials in formal variables. So what I mean by this is just take letters t1 up to tn, and then you start to build words in these letters by just considering arbitrary products in the t's, and then you consider linear combinations, and all this together forms the space of non-commutative polynomials. So it's just a kind of abstract function space. And then you consider the mu x, the non-commutative distribution, as a linear functional on this space. And how is it defined? You just take any monomial, well, you define it by linear extension, of course, and so it's sufficient to consider its value on monomials. So let's say one monomial, which is then of the form ti1 up to tik for some k, and this you simply map to phi applied to the same product, the same monomial, if you like, but in the operator. So that the indices I prescribe an order in which you multiply your operators, and especially which operators you are going to multiply, and then you just apply the phi to it. And this is in analogy to the classical probability language called a moment. So the mu x simply encodes all the joint moments of your operators or your elements in the algebra A, the x1 up to xn in A. And well, just to simplify the notation, so this space in the following, I will simply denote by C, T, where T, just little t, simply stands for the n tuple of formal non-commutative, formal non-commuting variables. Okay, so this is again a very general concept, and one example in order to see that it makes sense or that it fits into or that it corresponds to the classical notion of a distribution. So let me explain it in the following example. So if we have an n tuple of classical bounded random variables in L infinity omega f p, so we are going to have an n tuple, then so what I have to understand is the expectation of a polynomial in my tuple x, and the fact is that this is nothing but the integral over Rn p. So let's say our random variables are real random variables, so maybe I should be more precise by putting an R here. Then I just get the ordinary distribution, and this holds for all polynomials, but now in commuting variables, because classical random variables commute, so it doesn't really make sense in which order you multiply. So you can just evaluate commuting instead of non-commuting, or commutative polynomials instead of non-commutative polynomials. And just to explain it, or just to make it precise, what I already said, where this measure mu x is defined for every, let's say, Borel subset of Rn by just taking the probability measure of all omega in capital Omega such that x of omega, so the full tuple, so you just evaluate all the random variables at once, you consider the vector in Rn, and then you ask whether this belongs to the set B, and this happens to be a probability measure on Rn, and this is what is classically called the joint distribution. Distribution of the axis. And what this tells us is that having this in the background, it's quite natural to define or to call this object here the non-commutative distribution, because it really imitates a kind of construction which naturally leads in the classical context to what is considered there as the joint distribution of your random variables. It's really this formula here which bridges from the classical concept of the joint distribution to this non-commutative concept, and you see that things fit together. And it's again in the spirit of this non-commutative or building up a non-commutative theory that I mentioned at the beginning. You just try to formulate things without reference to the underlying space, or just try to formulate things only in terms of functions over the space and not elements of the space itself. So this is encoded in this way. So this is what we consider the non-commutative distribution. And as I already said, this structure is quite general, and it encodes many examples, especially algebraic examples, which don't have much structure and which are not really suitable for, well, analytic questions. So from that point of view, it's better to have non-commutative probability spaces with a slightly more structure, and more structure in the sense that it allows you to do analysis on the space. So we need a kind of topological structure for some of the purposes. And in order to speed up the procedure at this point, I have written down the definition that I want to tell you. So what are typical or prominent examples of these analytic non-commutative probability spaces? They are C star probability spaces and W star probability spaces. Okay, so by a C star probability space, I simply mean a non-commutative probability space where the tuple A, phi has the additional property that A is actually a unital C star algebra and phi is a state. So if you know what a C star algebra is, it's fine. If not, just think of a subalgebra of B of H, the bounded linear operators on some Hilbert space, which are closed with respect to the norm topology. So just closed in a suitable sense. So this is the notion of a C star algebra. And a state is simply a positive and unital linear functional on the C star algebra, and positive in the sense that it maps positive elements in the C star algebra to positive elements in the complex numbers, just positive reals in a sense. So to make it precise, so positive simply means that every element which is of the form A star A, and this is exactly how positive elements in the C star algebra look like, are positive, and this for all A in A, or I should better say more precisely say non-negative. Not the phi could vanish on some of them, but we require that it's non-negative. Okay, and then if you want to do other things, let's say in the von Neumann algebra context, then you typically work with a W star probability space, and sometimes you would be more precise by calling it a tracial W star probability space, but I just omitted this technical term for simplicity. So what I mean by this is in the same manner, a classical probability, a general non-commutative probability space where the A, the algebra, is now a von Neumann algebra, and the phi is again a state, but it's in addition faithful and normal and tracial. Faithful and normal are not so important for the moment. It's just, yeah, the faithful simply means that the phi can see every positive element. Normality is a kind of very special continuity, and traciality is just the fact that the product, the phi of AB is just the phi of BA. And just to say a word on von Neumann algebras, so if you don't know what a von Neumann algebra is, just think again of a subalgebra of B of H, the bounded linear operators on some Hilbert space, but instead of the norm topology, we just take the closure with respect to some locally convex topologies, namely the strong or the weak operator topology. And I can say or because at the end it turns out that it doesn't make a difference. So both topologies have the same effect; they lead to the same structure. So just think of another kind of closed algebras. So this is what we consider as analytic spaces on which we can do more sophisticated things than just these rather algebraic constructions. But I should also say that already in this very algebraic framework, you can say a lot. I mean, free probability especially can be formulated to quite some extent already in this abstract framework, but I will focus now more on the analytic side. So after this, so the question might be, what is it actually good for? So what is really the purpose of having more structure in the underlying space? And the reason is the following thing. Namely, we have the following definition. So let A, phi be a C star probability space. And what I want to tell you is that in this particular setting, this abstract object of a non-commutative distribution can be replaced somehow by a measure, like in the classical probability setting. Because remember, this abstract concept of a non-commutative distribution actually boiled down to a measure on Rn, so a very classical, very nice analytic object. And the question is, do we have something like this also for non-commutative distributions in general? And the answer in general is no, because even if you impose this additional structure of a C star probability space or W star probability space, you still have this non-commutativity around, which doesn't allow you to encode this full non-commutative distribution by a single measure. So one measure is not enough. But there is one particular case, well, there are actually two, but I will focus on this, on one example, namely the example where we have a self-adjoint operator and actually one operator, and then things work out nicely. So let's say for a single operator X, which is self-adjoint. So remember, on a C star algebra, we just have an involution star, and we call an element self-adjoint if it is preserved. It's a kind of fixed point under this involution. It's like in matrices, the complex transpose, or on the algebra of n by n matrices, the star is precisely the complex transpose. So on a matrix, a self-adjoint matrix would just be an Hermitian matrix. For such an element in A, there exists a unique Borel probability measure, and we call it again mu x. Of course, it's abuse of notation, because mu x would stand for the non-commutative distribution of the single operator, but you will see in a second why it's a good idea to do it like this. So we have this measure on R, such that the following condition holds, namely that phi of xk, so we just consider moments of our operator, and in a single variable case, all moments are just of the form x to some power k, and the thing is that these moments, these numbers can be encoded by this probability measure in the sense that these numbers are precisely the moments of this probability measure. So if, so this phi of xk, these are just the moments which are encoded by the non-commutative distribution, and they are given now as the moments of this measure for all k from 0, 1, 2, and so on. And well, the existence is just well, a consequence of the Riesz representation theorem. Anyway, functional analysis details. And we call mu x the analytic distribution of this operator x. So you see, in this case, the situation is not so bad. We are still in a non-commutative setting, but as long as we work only with one self-adjoint operator, we can still encode the non-commutative distribution by a very classical object, namely a measure on R, and this is the analytic distribution. And it's somehow a very interesting task to, well, many questions in free probability especially are around distributions, or what can be said about such analytic distributions. And so it's good to have a good understanding of this object, and maybe it might not be so clear what this object or how this object might be related to other things you know. And so maybe let me give you the following note. In case that you, so in the particular setting that A phi is not only a C star probability space, but actually a W star probability space, then the mu x, this analytic distribution is nothing but the composition of our trace phi with the resolution of identity of our operator x. So let me just write it down, where Ex is resolution of identity for x. What you're doing is you just take the functional calculus, the Borel functional calculus for x, and then you just apply, or this allows you basically to write, maybe just as a side remark, it roughly allows you to write xk as the integral over a t to the power k, and then with respect to this projection valued measure Ex, integrate with respect to t, and then you just apply the phi to this identity. On the left, you will get precisely the phi, which is the left-hand side here, and on the right, you will get, here phi of Ex of t. This is then exactly the measure which you must have here. So just applying phi to this identity here leads you to here, and hence this object must be the distribution as claimed. So this is, as I said, just a consequence of this functional calculus, and hence it shows you that some kind of interesting structure is hidden in the non-commutative, in this analytic distribution, which might be interesting for operator algebraic questions. So this is what we this is the object of interest. So we have set up what the underlying objects are, what non-commutative probability spaces are. We have explained, or we have seen that somehow the analytic distribution or the non-commutative distribution of operators is interesting, or might be interesting. And the question is, are there any tools to deal effectively with at least analytic distributions? And the answer is yes, there is an important tool. Namely, this is the Cauchy Transform. The Cauchy Transform allows you to deal in a very effective way with analytic distributions, and it can be seen as a kind of non-commutative analog of the Fourier Transform, or if you want, the logarithm of the Fourier Transform in a sense. And it's a concept which also appears in random matrix theory, even before it was noticed that there is actually a connection to free probability theory. So there it's typically called the Stieltjes transform, and the difference is usually only a sign in front. So what is this important object, the Cauchy transform? So here, my initial object is that of a measure, and this measure could be just the analytic distribution. But here, just for simplicity, I work with any probability measure on the reals. And as notation, let me introduce the upper half plane C plus in the complex number. So this is the set of all complex numbers Z, for which the imaginary part is positive. So it's just the upper half plane in C. And well, it's good to have also the notion of a lower half plane. So there we will just put the minus sign, and well, the notion is just here. Instead, we put a minus sign. So it's just the C minus are just the complex numbers with negative imaginary part. And then you can define the following function, capital G of mu. And what is this? This is a function defined on C plus and taking values in C minus. And what you do is you just take a point set in the upper half plane, and then you integrate the resolvent 1 over z minus t, just this rational expression, with respect to the measure. And of course, well, you must check that it's really, that it's well defined, but this is not a problem, as one actually finds that the function over which you integrate is bounded, so everything is nice, so it's really integrable. The resolvent here is really integrable, so this integral makes sense. And then you can check that it really maps the upper half plane to the lower half plane. This is an easy exercise. And then you can check in addition that this is not just any function, it turns out to be a holomorphic analytic function. And this is exciting, and this is really great, because now you have somehow opened the door to complex analysis. So you can really use the toolbox of complex analysis to deal with them. And this is actually, well, a rich source of results. But well, for the moment, just take this definition as it is. And just as a side remark, as I said, this is a general definition which works for every Borel measure, but the measures which we are interested in are precisely or typically the analytic distributions of self-adjoint operators. So typically, or quite often, we consider the Cauchy transform of the analytic distribution of an operator X living in a C-star probability space, let's say. And then the question is, can we make somehow a relation to the operator? So by definition, it's just the integral with respect to the analytic distribution. But then if you go backwards, what it really is that this can be written as the expectation of the resolvent of the operator. So a self-adjoint operator has spectrum in the reals. So in particular, for every complex number in the upper half plane, this z minus x. So in order to be more precise, you should maybe put an identity here. So z times the identity minus x is always an invertible operator, provided that z belongs to the upper half plane. So you can take the inverse. This gives you a bounded operator in your C star algebra, and then you just apply the phi to it, and this gives you a complex number. And this is really the value of the Cauchy transform at this point z. And well, as I said, this holds for all z in the upper half plane. And for that reason, since we have this relation and since we can write somehow the Cauchy transform in terms of this object here, it's sometimes convenient just to write this as the Cauchy transform of the operator and not of the its analytic distribution, but this is just notation. So it's just the same. So we just consider the Cauchy transform of an operator as the Cauchy transform of the analytic distribution, or typically define it in this way. But at the end, everything is equivalent. But still, so far, we only have associated an analytic function to a non-commutative, to an analytic distribution, to a Borel probability measure on R. And actually, the restriction to probability measures are not really important at the moment, but it's just a convenient setup. But the question is, can you also go backwards? So if somebody gives you a Cauchy transform and doesn't tell you what the underlying measure is, can you reconstruct the measure from only knowing this Cauchy transform? And the answer is yes, in a weak sense. And to make this precise, I give you the following theorem. And this theorem is what is called the Stieltjes inversion formula. And what do I mean by this? So starting with the Cauchy transform of the measure, we define a family of probability measures, namely by d mu epsilon of t. So these are going to be absolutely continuous probability measures, so meaning they have a density with respect to the Lebesgue measure. And we define this to be 1 over pi. And actually, we have to add a minus sign in front in order to have a positive measure. And what we do is we take the imaginary part of the Cauchy transform at the point t plus I epsilon, and then we integrate. We just put the ordinary Lebesgue measure there. So just think we have our complex plane. And in the complex plane, we have some line parallel to the real axis, let's say in distance epsilon, and we just take the values of the Cauchy transform on this axis, or actually minus 1 over pi times the imaginary part of this Cauchy transform there, and then it turns out that this is a probability measure. And what is really important is the following. Namely, then we have that the limit, if epsilon goes down to 0, of these integrals here. So if I take a, let's say, bounded continuous function on the reals, then I can integrate these functions with respect to each of these measures mu epsilon, and then I take the limit, and in the limit, what I get is precisely the integral of the same function, but with respect to the measure mu. So in a sense, we have a kind of convergence of the mu epsilon, the mu epsilons to mu, but in a weak sense. So it's a weak convergence in this sense that I've written down here. So in this sense, we are able to recover the measures, the underlying measures from the function, this analytic transform, and this is why it becomes a very important tool in the computation of analytic distributions. And just to give you an idea how this would work, so somebody would give you a Cauchy transform, and then you would just compute these measures for some small epsilons, these approximations for small epsilons, and then this will somehow show you how well, this would give you an absolutely continuous approximation of the actual measure, and then you would typically be satisfied by just computing the density. And this would already tell you a lot about this measure. But you should still keep in mind what you can really compute somehow, or at least numerically, if you do it in a numerical way, are these as absolutely continuous approximations. We will see examples in the sequel. But still, we have the feature that we can use this to as a kind of analytic machinery to compute these distributions. But now it's maybe time to show you one very prominent example of a non-commutative distribution, and this is the semicircular distribution.
Can I ask,
sure.
This previous theorem, it's just about any measure on R or some kind of
positive measure on R, right?
And you don't see, it's not something, it's the classical thing, right? It's not something that you come and then that you get from the non-commutative.
No, it's a very classical theorem, classical analysis stuff. It doesn't have to do anything with the non-commutative world, but I'm just saying that it has very important applications in the non-commutative world. That's the purpose, yeah.
So what would happen if you do the same thing in the classical setting, like a random variable, and you take this distribution? Like, what does it give? And like,
I mean, you could, of course, use the Cauchy transform also in classical probability theory, because I don't refer to any kind of independency. I'm just using the distribution, and if your distribution might come from a classical random variable, that's fine. You would just have the same result, but of course, then you must have tools inside classical probability theory to compute the Cauchy transform. But the point is that in classical probability theory, usually it's easier to compute the Fourier transform instead of the Cauchy transform. While in the free world, at the moment, I haven't told you what free probability really is, just the underlying setup. But there it turns out that the actual object are, or that a good object are the Cauchy transforms, because they behave much nicer with independence than the Fourier transform, while the Fourier transform behaves nice with respect to classical independence. So you have really these two sides. Mm-hmm.
So when you say Fourier transform, you mean like, where is the group? Or where?
Oh, I mean just the ordinary, so functions on the real line. You just take, you integrate your functions with respect to the exponential kernels, e to the power itx. This is what I mean by the Fourier transform.
I mean just the Fourier transform of this. Okay, and in the non-commutative case, you have some difficulties with it, and instead, this is like an approximation of the Fourier transform.
It's in a sense related to the Cauchy transform, but in the as I said, it's more like it's more that the independence forces you to work with a different kind of notion. I mean, the Fourier transform behaves nicely with respect to classical independence, and the Cauchy transform behaves nicely with respect to free independence. At the moment, I totally admit it's not clear why one should look for another kind of transform. So you must believe me that this is really the case. So for the moment, it's just this abstract object, which I'm somehow advertising as the tool for free probability harmonic analysis. Okay, does this answer your question? Okay, excellent. So let me go to the semicircular distribution again. So there I'm having, what I mean by the semicircular distribution is just a measure on the real line, which has a density with respect to the Lebesgue measure, and the density is just shown in this picture here. Well, it doesn't really look like a semicircle, but this is just due to the scaling that I have. If you look here, this is the definition, this measure sigma, which I'm going to, or this is how I'm going to denote the semicircular distribution. It has a density with respect to the Lebesgue measure, and the density is just the scale semicircle located on the interval from -2 to 2. So this is just a measure. And if I have inside some C-star algebra a self-adjoint operator, let's say S, whose analytic distribution happens to be the semicircular distribution, then I call this operator a semicircular operator. And again, I already advertised the Cauchy transform as a very nice tool to deal with distributions in free probability. So maybe it's good to have a kind of characterization in terms of the Cauchy transform. And in fact, you will see that the Cauchy transform of the semicircular operator satisfies this quadratic equation. So whenever you have a Cauchy transform satisfying this equation, it must be the Cauchy transform of a semicircular element, or it must be the Cauchy transform of the semicircular distribution. So this is just another point of another way to look at a non-commutative, another way to look at a semicircular distribution. Okay, we will come back to this. But now it's really time to explain you what actually is the notion, this mysterious notion of free independence, which makes free probability appear. And again, like in the underlying setting, it's better to look at the classical notions before. So in classical probability theory, if you have bounded measurable functions which are classically independent, then what you can do is you can compute the expectation very easily of x to the power n times y to the power m. Well, and it's very easy in the sense that this just factorizes. So what you get is the expectation of x to the power n times the expectation of y to the power m, and this for all m and n non-negative. And the same, or well, a similar kind of rule, let's say, underlies the definition of free independence. So here we take just a non-commutative probability space, and we say that a family of subalgebras, and I just take some arbitrary set as an index set, and the AIs are just unital subalgebras of A, and these are called free, or well, more precisely, freely independent, if the following holds, namely if for every choice of an integer, non-negative integer n, and for every choice of n indices in our index set, which satisfy the property that neighboring indices are different, meaning that I1 is not equal to I2, and this is not equal to I3, and so on. And the IN minus 1 is not equal to, this was wrong, sorry, to IN. So I'm just requiring that neighboring elements are different, but I'm allowing that maybe the first and the third index are equal. So this is allowed. Only neighboring elements must be different. And then what I'm doing is I take a non-commutative random variable AK, which lives in the ikth algebra, and I impose the condition that the expectation of my AK is 0, and I impose this condition for all k from 1 to n. And then whenever I have this, it should follow that the expectation of this product happens to be 0. So in a sense, the expectation, the expectation of a product of centered elements, which are coming somehow from alternating algebras, must be 0. So this is somehow the notion of free independence. And if you see it for the first time, I totally admit that it might look quite artificial. So why is this really a justified definition? And in a second, I will explain or try to explain why it really makes sense. But before doing this, let me just give you the second part of the definition. So this is how we call, or when algebras are called independent. And using this, I can do the following. So if I have now a family of non-commutative random variables, let's say, of course, in A, this is called free if, well, just the algebras generated by the identity, the unit element in A, and the xi, so all these algebras are free in the sense of 1. Well, this is just a matter of notation. So first you define what you call, or you define what you mean by free algebras, and then you use this terminology to define when the elements xi are free. So what it really tells you is a kind of relation among the expectations of products of your x's, in a sense. And if you think a little about this, what it really means is the following. Like in classical probability, or like this, like for the classical independence, free independence provides a rule to compute mixed moments. And I should better write rule in quotation marks, to compute mixed moments. What I mean by this is, let's say you have a family of non-commutative random variables xi. You know that these operators are free, and assume that you know all the moments of this xi, of these xi's individually, and then free independence allows you to compute mixed moments, so where you just take products in your x's, arbitrary products in the x's, out of the individual moments of the xi's. For instance, if you have an x and a y which are free, then how do you do, what can you do? So how can you compute the phi, let's say, of x comma y, of x times y? So what you would do is you would just use the free independence. The free independence tells you that the expectation of x minus its expectation, because in general you don't know anything about the expectation of x, So we must center it by just subtracting the expectation of x. So this now, so this element here happens to be a centered element, and we do the same kind of centering procedure for the element y, phi of y times the identity. And then you have a product of centered elements which are coming from different algebras, and they are free, and hence by the freeness condition this must be 0. But then what you can do is you can just start multiplying this out, and what it gives you is that you get phi of x times y, and then some cancellations appear, so minus phi of x, phi of y, and from this you get that phi of x, y is just phi of x times phi of y. And then knowing the expectations of x and y individually, this allows you to compute via the freeness assumption the expectation of the product x times y. Excellent. But this might give you the feeling that we are not that far away actually from classical independence, because we still have a kind of factorization. But this is not quite true. You can, well, it's not true at all actually. You can make more complicated examples. And this one is somehow the most basic examples where things become more complicated. So if x and y are still free, then you can do the same kind of computation. But of course, it becomes more complicated. But then you end up with the following rule. It's phi of x squared times phi of y squared plus phi of x squared, phi of y squared, and then minus phi of x squared, phi of y squared. So you see, things become slightly more complicated in this way. And provided, and it also tells you that freeness is really somehow the domain of a very high non-commutativity. Why this? Because imagine that the x and the y would commute, then you could write this as phi of x squared times y squared, and then you could use the result from 1, which would tell you that you can write this as phi of x squared times phi of y squared. But this is not true. So the rule here is more complicated. And this really tells you that variables which are free are far from being commutative in this sense. But of course, there is much. Yeah.
What would this condition mean for matrices to be free?
Actually, matrices, you cannot come up with free matrices in this sense. So it's still in this sense, you could say matrices are already still too commutative to be free. You still have too much commutativity, so you can never make this happen. So it's really a kind of abstract notion so far. But, and this is somehow the crucial thing behind random matrix theory and the connection of free probability to random matrix theory, that in the limit you will make appear this relation. But of course you have to deal with random matrices, not only matrices. But then you will really see in the large n limit these kind of relations. I
guess you can also take some trace class infinite dimensional operators, right? And
you can, well, I mean, you can also come up with operators which satisfy this property, of course. You don't have to come up with random matrices to see this. You can build, you have some kind of Fock space construction. We will also see this. I will come back to this in a few minutes.
I just wonder if there's some kind of a simple, like typical example of being freely independent to freely independent variables.
Again, you will see it in 1 second. Indeed, that's a very important question. So where actually does the free independence come out? And actually, why did Voiculescu? I mean, this is the name. This was the founding father. I mean, he developed around the year 1985 free probability. He came up with this notion of free independence, And since then, this field developed, and it's still developing. But the question is, why did he come up with this notion? And the reason is that he was interested in free products of groups with the so-called free group factors. And in order to make this a little bit more precise, let me give the following definition, or let me try to explain you what I'm doing. So we start.
Let me just interrupt you once again.
Yeah, sure.
About just the timing expectations, the non-commutative expectations. Like, how long do you plan to go now?
I mean, I was planning to. I noticed that.
Feel free, because we're recording it. So if someone in a rush to leave, you can leave. And
I know that I'm already above 1 hour, but I said something like 90 minutes. Would this be okay, or is it already?
Sure.
Okay.
Yeah, I just wanted to set some expectations.
Yeah. Okay. That's the purpose somehow. Okay. Yeah. Discrete group, and by little e, I denote the neutral element. And then what I'm considering is the group algebra Z of G. This is just notation. And by this, I mean just the set of all functions defined on the group, taking values in C. And the only requirement is that the number of elements on which this function alpha takes a non-zero value is finite. So this is this. And on this algebra, I define a multiplication by convolution. Well, there are several ways to do it, but this is the way I'm going to define it. So as a kind of convolution, I'm summing over all h's, h and g, and then I'm computing alpha g h inverse times beta of h. So this is the multiplication on this group algebra, and then I define a kind of expectation on the group algebra. We're just taking an alpha and sending it to the value this alpha takes at the identity. And in this way, of course, I'm getting the G, this tuple, which happens to be a non-commutative probability space. And so maybe it's helpful to keep in mind that this group algebra is actually spanned as a linear space by functions delta g, where g runs through the group, where this delta g is simply the indicator function at the point g. So if my h is g, I assign the value 1 to it, and if h is different from g, I get it like this. I get back the value 0, and then the multiplication becomes a little more transparent, because what I get then is just the indicator function of the ordinary multiplication. So in this sense, I'm just implementing the multiplication coming from the group in this group algebra. And then we have the following theorem. If I have subgroups G1 and G2 of this discrete group, which are algebraically free, in the sense roughly that G1 and G2 have nothing in common, especially no relations in common, then just the commutativity with the identity, so the usual cancellation rules in there. And then I can come up with the group algebras G of Z of G1 and Z of G2 inside this larger group. Of course, these are functions, so you should think of Z of G1 sitting inside Z of G just as an extension by 0. So the elements in here are just functions on G1, and then you can just extend it by 0 to functions of G, and everything works out nicely. And then it turns out that freeness is really this algebraic freeness is really encoded by free independence. And just to make this transparent, let me indicate the proof or sketch the proof. So if you have elements like this and alpha g's, which come from these group algebras, and you impose the condition that alpha k of the identity, the unit element, which is nothing but phi g of alpha k, is 0. And then what you do is you must compute the expectation, the phi of the product of these alphas, so just a convolution of these alphas. And then, well, by definition, this is just the value of the convolution at the identity. And then you just write down what it means. The convolution can be written like this. You just sum over all elements, G1 up to Gn in G, alpha 1, G1, alpha n, Gn. You just have to write down how the convolution is defined, and then you see that it's really like this. And of course, sorry, this is the other condition, of course, that the G's, the product of the G's is just the neutral element in the group. And then the following happens. Since the alpha i's are supported on G i's, this condition here, so this term is only non-zero if G1 belongs to the group Gi1. And this must be non-zero in order to have a non-zero contribution, and this enforces this element Gn, well, actually this holds for all Gi's, this element to belong to the group Gin. But then, since the product of all these elements must be the identity, and since the groups are supposed to be algebraically free, the only way to come up with a product of this type is that you have somehow at some position the neutral element. Otherwise, you would only have elements coming from different groups, and since there are no relations among the parts, among the elements coming from the different free groups inside G, there couldn't be any cancellation which would bring you back to the neutral element, and hence at some position, somewhere in this product, G1 times G2 up to Gn, you must have an identity sitting. Otherwise, there wouldn't be a chance. So this means there exists a k such that the element Gk is the identity. But then, again, by this definition here, we must have that d alpha is 0, and hence this whole sum, this whole summand is 0, and since this holds for all summands, since this holds for all summands, the full sum must be 0, and this is how you get the freeness condition back. Okay, I admit that this was rather quick, but I only want to convey the impression that coming from this this question of algebraic freeness, it's, well, I'm not saying that it's obvious to come up with the notion of free independence from there. I mean, this was the ingenious observation by Voiculescu that you can really make use out of this, that you can really treat this as a kind of non-commutative independence. But if you have this in the background, it becomes much more natural to look at this very particular kind of independence. And I think maybe it's better to skip this part. So because at the moment this was purely algebraic, but actually the question, the birth problem, if you want, so that the question which really inspired Voiculescu to come up with this was this famous isomorphism problem for the free group factors, and these are grouped for Neumann algebra. So what you're actually doing is you take this group construction, this group algebra that we have constructed, and you build up the left regular representation of this group, and out of this you build a von Neumann algebra, and you do this in the particular case of the free group factors, of the free group, and then what you get is the so-called free group factors. These are the von Neumann algebras associated to them, and you still have this freeness visible in the setting. And then, sorry, I must skip this. And then you arrive at this very fundamental question about free group factors, namely the isomorphism problem. So imagine you have a very concrete, but in a sense rather abstract, construction of a von Neumann algebra. You start with a classical group, namely the free group Fn or Fm, the group which is freely generated by elements G1 up to Gm. And then you build the group algebra, and out of the group algebra, the von Neumann algebra. And then you have a very abstract object. And the question is, do these abstract von Neumann algebras still memorize the number of generators inside the group from where you started? So meaning that if you have m and n different integers m and n larger than 1, because in the one variable, if m or n is 1, the associated von Neumann algebra will be commutative, and then the question becomes trivial because the other free group factors are never commutative. So it's clear that the question is only a question about these non-commutative examples of von Neumann algebras. And there you ask, is it necessarily the case that if I have an isomorphism between two of them, that the indices, the number of generators, are the same? And the fascinating thing is that this question is still open, but this was really the starting point why Voiculescu began to develop free probability theory. And this sounds like bad news, but this is not true at all, because since then, many deep insights to this problem have been found. And one of the things that I want to share with you is this fundamental theorem, which was found independently by Dijkema and Radulescu in 1994. And the statement there is that still we don't know what is true, whether the group factors are isomorphic or not. But we only have the following two options, namely either all of them are isomorphic. So this group for Neumann algebra construction completely forgets about the number of generators, or they are all different. And this means it cannot happen that you have some kind of islands of isomorphism, meaning that you have a few indices for which they are isomorphic and some other indices for which they are different. So you either have all of them different, or you have all of them being the same. And well, the surprising thing is that this result actually makes use of another very important consequence, and another very important result of free probability, namely its connection to random matrix theory. And this
Tobias?
Yeah, sure.
Could you please check the connection of your mic if it's a loose connection? Something changed.
Okay. Maybe.
Or I don't know. Maybe Thank you.
Okay, I will try my best.
Oh, that's great. Thank you.
Okay. Okay, perfect. Thanks for letting me know. Yeah, so the reason is that free independence, even though inspired by this group algebra problem, let's say, actually has connections, or this abstract notion of free independence has other sources. As I said at the beginning, there's another, or earlier before, there is another construction named the construction of full Fock spaces, in which you can appear free independence out of orthogonality. I'm not going into this direction, but it's simply another kind of construction to produce free independence. But much more important is actually the connection to random matrix theory. And there it's more important in the sense that it comes somehow as a surprise. It was not built according to classical independence, but free independence turns out to be the large n limit in a sense of classical independence. So if you take random matrices and you blow them up, going to the limit, then you will see that independence turns out to be, turns out to turn into free independence. And the exciting part about this is that you have three sources, let's say, of free independence, and they can be treated within the abstract framework of free probability theory. But in this way, you also allow of an exchange of tools. So meaning that if you are interested in these operator algebraic questions, you can also maybe make use of these results inside the random matrix world, or you can make use of the random matrix techniques inside the operator algebraic world. And this is really this connection which underlies the result of Dijkema and Radulescu that I mentioned before. They really make use out of this strong interplay between random matrix theory and free independence. And in order. Yeah, so okay, here we go. Maybe I use this here. So what are actually random matrices? Let me try to be as precise as possible. So by random matrices, I again mean elements in a very special kind of non-commutative probability space, namely this here. And as I said at the beginning, these are just built up out of the matrices and classical probability spaces by the tensor product. And you do it like this, but at the end, it's just a non-commutative probability space again. But there's one technical subtlety. In order to include somehow random matrices of interest, you must modify the underlying space, which so far were only L infinity functions by L infinity minus functions. And these are just random variables having all moments of all orders. So this is less restrictive than being a bounded random variable. So in particular, it includes the Gaussian distribution. And having this, you can come up with the Gaussian random matrices, which are modeled inside this framework. And what do I mean by a Gaussian random matrix? I simply mean a matrix a self-adjoint matrix, a mission matrix if you want, whose entries form a complex Gaussian family, and you only must specify the covariance of these entries. Well, I mean, just imagine you have an n by n matrix, and for each entry you choose a complex Gaussian random variable as an entry, but you impose the condition that the matrix happens to be self-adjoint, and you impose a normalization by putting a normalization by 1 over n in front, in order to make to give it the right limit behavior. Let's say it like this. And then what you are asking is what is the limit? What are the eigenvalues of these matrices? So this is the typical question in random matrix theory. You take a self-adjoint random matrix, you compute the eigenvalues, the lambda 1 up to lambda n. These are random variables because they still depend on the concrete realization of your random matrix. So you just realize it once, and then this will give you a matrix, and you compute the eigenvalues of this particular outcome, and you compose these eigenvalues as a measure like this, and this you call the empirical eigenvalue distribution. So it's just a measure, an atomic measure where each eigenvalue is an atom with weight according to multiplicity. And in this way, you get a random probability measure. So it's not only a probability measure, but it really depends. It's a random. It's random. It's not a deterministic measure.
That's kind of that's what they do in quantum mechanics, right?
Right. It's a very canonical construction, but then you can make it deterministic by saying, okay, I'm not taking a fixed realization of the matrix. I'm just taking the average. I do it several times, and then I just take the expectation of it in this sense. I just average, and then I get the average eigenvalue distribution, which then is a deterministic measure. And I mean, this line is not so important for the moment. It should only tell you that somehow this average eigenvalue distribution is really the distribution in the sense of the non-commutative distributions that I introduced before. So again, we have a nice connection of this abstract language to another classical or well-established concept. I mean, so it's just this line.
Can I ask you, can you go one slide above?
Yeah, sure. You mean here?
So you have this first definition, and then you have an example, and is it
right?
And is it clear? Is it the same, or it's an example of a more general thing, or because it looks like in the first line you have like a same measure at every entry, and here you have some independence.
No, I mean, that's the point. I haven't really specified the underlying classical probability space, and this is not really necessary. You just think that these independent entries are realized over a common probability space. You just
like a model for your
exactly.
The thing you get in the non-commutative.
Exactly. It's For instance, you could also think of just taking the n by n matrices, and then you just put a Gaussian measure on the space of the random, on the space of matrices. This is a very particular way to come up with such an underlying probability space, but I find it more confusing at this point. Just think of a space on which you can realize your Gaussian family by which you fill up the matrix.
But does it have to be Gaussian? Can you take like any measure, like in the first line? And
yeah, you can do whatever you want. I mean, you can build up random matrices with arbitrary entries, and you can make it non-self-adjoint. You have a huge playground in this way. But for instance, if you a kind of a canonical generalization of the GUEs are Wigner matrices, where instead of the Gaussian distribution, you allow a general distribution, but still you have this kind of independence and the self-adjointness condition that you impose. Then you call such a thing a Wigner matrix, and actually many of the results that I'm going to tell you, maybe in the remaining minute, are going in the same way. So you won't see a difference, but the starting point are typically the GUEs, and they are the most prominent examples, actually. Yeah, but you're right. It's not exclusively the GUE situation. It works more generally. And in order to make it transparent, what we are actually doing here, let me show you this example here. So how would it look like? You just take a GUE matrix, let's say of size 5. You have a 5 × 5 random matrix. You realize it once and you compute the eigenvalues, and then you would plot the histogram and you wouldn't see much. You would just have the 5 eigenvalues there. And then you do it with a 10 by 10 matrix, and then you would again have 10 eigenvalues. But here you would see that at least in one bin, you would have 2 eigenvalues, and then you have, but apart from this, you have just isolated eigenvalues, let's say. But then things become more interesting if you increase the size. So for n equal to 100, you see something like this. And for 10 equal 1000, you see something like this. And then it happens that, well, you notice that a kind of limit shape appears. Namely, you will see that in the limit, if you increase the size, the shape of this histogram begins to look like the semicircular distribution. So what the surprising thing is that in the large n limit, randomness seems to disappear for the eigenvalues, and the eigenvalues seem to become deterministic, or seem to have a deterministic behavior. And this is really the result of Wigner's theorem, saying that we have distributions that the empirical eigenvalue distribution, well, actually, it's there's a step in between. Typically, you would show it first for the average eigenvalue distributions, but then by some more detailed analysis, you would see that it also works for actually for the empirical eigenvalue distribution, so not only for the average one. And this is the result I'm mentioning here. And this is actually what the pictures show you. So almost surely you would see that the measures, the eigenvalue distributions, converge to the semicircular distribution. And in other words, you could say that the random matrices themselves converge towards a semicircular operator in distribution. At the moment, this is just language. We're just rephrasing this kind of convergence by saying that either we say that the eigenvalue distribution converges to the semicircular distribution, or we say that the random matrices themselves converge in distribution towards a semicircular operator. But this has a very strong conceptual consequence, because this allows you to understand the following result, which is Voiculescu's fundamental result about asymptotic freeness. And it simply tells you that if instead of only one variable, you begin to work with more random matrices and you impose the condition that they are independent realized. And then you look at the limiting behavior of this full tuple. And the surprising consequence is that in the limit, this n tuple of random matrices will be modeled by a tuple of freely independent semicircular operators. What this tells us is that we have in the limit a kind of, well, that freely independent semicircular elements provide an operator theoretic model for the limit of independent Gaussian random matrices. And this has strong implications. And but before I say a word on this, let me just say this is the source of free independence inside random matrix theory that I mentioned before. So more or less out of nothing, of course, there is a conceptual reason for this, but more or less out of nothing, you see free independence appearing out of classical independence. That's totally surprising, especially if you keep in mind where free independence comes from. Free independence comes from this notion of the free group, these group algebras associated to free products or whatever. And here we see it in a totally different context appearing in a very natural way. That's surprising. And maybe to finish, let me say what kind of consequences does this have, and this actually leads us more or less to into the direction of Roland's talk. The thing is that if you know how the limit of random matrices is determined, maybe it's determined by these freely independent semicircular elements, you can ask more sophisticated questions. So if, for instance, you build up out of your random matrices more complicated random matrices by just evaluating non-commutative functions in your random matrices. The most fundamental example would be you just take the sum of two independent Gaussian random matrices, or you take a product of independent Gaussian random matrices, or more complicated polynomials, or more complicated functions. And then this statement says that the limit distribution is given by the analytic distribution of the same non-commutative function, but evaluated in freely independent semicircular elements. And this allows you to use free probability machinery to compute actually this limit. And hence you can you can open the toolbox of free probability for random matrix questions. But what is interesting is what kind of non-commutative functions do we have in mind? The first example are the non-commutative polynomials, which we have already seen. Then there is something which is called non-commutative rational functions. I'm not going into this direction for now, but more interesting for the moment is, and especially important for Roland's talk, are linear pencils. And what I mean by this is you just arrange your GUE matrices inside a larger matrix as blocks, or in abstract terms, you just take tensor products of this form where the coefficients are just self-adjoint matrices. And in this form, you build up a larger matrix. So it happens to be a k times n times k times n random matrix. But still, you can ask, okay, what is the limiting behavior? And still, the limit is governed by a kind of operator of this form here, where again, your random matrices are replaced by the limits of these random matrices, namely semicircular operators. And then what you get is an operator-valued semicircular element. And from there, you would begin to develop what is called operator-valued free probability. I won't go in this direction, but what I want to tell you is that
A is anything?
It could be any scalar but deterministic matrix and self-adjoint, nothing more. You just take whatever you want. Yeah.
I mean the algebra A.
Oh, sorry, this algebra A, sorry, I forgot to say this. This is the algebra of random matrices. So this is the space in which your initial random matrices live in. So, I mean, if you allow me to go back.
Okay, so that's confusing. You tensor matrices with matrices.
Exactly. Yeah. Or another way, I'm just arranging these matrices as blocks inside a larger matrix. This is what I'm doing. Okay. Yeah. And then, as we said, here we go. The limit object is then this very particular operator, an operator-valued semicircular element. And operator-valued free probability allows you to compute or to tell you a lot about the Cauchy transform of this object. In particular, allows you to compute it in a very efficient way. And the reason is that one has also something like an operator-valued Cauchy transform, and it's now taking values, or it's defined on a matrix upper half plane, and it takes values in the matrix lower half plane, and the matrix upper half plane and lower half plane is basically defined like the upper and lower half plane in the complex plane. You just take the matrices whose imaginary part is positive, and this is the upper half plane, and one additional constraint: the imaginary part as a matrix must be invertible. So this is just to be sure that you are really staying away from, let's say, the real axis in this larger space. And then surprisingly, you will see our old friend, this quadratic equation for the Cauchy transform again. But now it's a matrix equation, and there is a function eta showing up, and this eta is, which implies or it encodes the coefficient matrices A. The A's, remember, are the coefficients in front of our semicircular elements, which build up then this operator-valued semicircular element, and they together form this map eta, and this is the only information which is needed to compute this particular Cauchy transform, or at least it's the only information which appears in this this quadratic equation here, right? And then you might say, okay, this is just equation. It's just an equation, but can you make use out of this? And indeed, you can make use out of this. And this is the last thing that I want to tell you. You can actually solve this by a very efficient analytic machinery. And Roland is going to tell you more about this on Monday. It's a result of Helm, Rashidi Farr, and Speicher, saying that you can actually use a kind of fixed point iteration to compute the Cauchy transform that you're interested in a very efficient way. It's actually this result here. And then out of this matrix value Cauchy transform, you just evaluate it at a scalar multiple of the identity. And what you get back, if you apply the normalized trace to it, is precisely the Cauchy transform that you are interested in, namely the Cauchy transform of this operator valued semicircular element. And then you are done. You have done some kind of detour via operator valued free probability, and in this way, this is the final picture that I want to show you, coming for a very particular example. Namely, you can compute the limit behavior of such block Gaussian random matrices. So let's say you have a very particular choice of coefficient matrices. So what this would mean, that is what this means is that instead, just think of the S1 and S2 and S3 here. That you put your random and your Gaussian random matrices there, and then you compute the eigenvalues of this larger matrix. And what you would get if you do it for n equal to 1000 is precisely this picture here. Okay, it's a little bit small, but you would see that here is a histogram, and of course here is also one part. And this is the eigenvalue distribution. But the question is, what is really this limit? Can we compute it? And then you turn on this machinery. You just compute the distribution of this measure of this operator valued semicircular element, the mu s, and this gives you really the limit shape that is shown here. So you see that free probability, the toolbox of free probability via this connection of asymptotic freeness enters random matrix theory and allows you to compute such limit distributions. And then, and this is the topic that Roland is going to cover in this talk, is you can actually go further, because this connection actually allows you to answer algebraic questions, because it actually tells you something of the functions that you are dealing with, and not only about the random matrices or the operators that you put in. And this is another that's another topic which begins at this point here, but I guess it's now definitely time that I should finish, and I should very much thank you for your attention. Thank you.
Okay, thank you. Let's thank the speaker. Well, let me just take you a few levels down to the last slides. Below the last slides. The semicircular distribution.
Yeah.
You see it really not as a distribution of something, but as a function that gives you some moments, which then you have some interpretation in terms of non-commutative moments, right? Is that right?
You have the 2 points of view. You can either say the semicircular distribution is this very particular measure, or you say that you prefer to work with an operator having this distribution, and depending on the question you are interested in, one or the other point of view might be more helpful. But it's right. It's just this.
At no point you get like a classical variable that this is its distribution. You just have a new, like in this new non-commutative definition, you look at some like power series and then you construct a function out of them. And this is the function that you get.
Yeah.
Okay.
In a sense, yes. Yeah. There are several ways to come up with distribution. So, how should I say? So, independent of whether you are interested in the measure or the concrete operator, having this measure as the distribution, the Cauchy transform really allows you to deal in a kind of uniform way with it. This is the analytic object associated with it, but you can actually also go the other way around. You can start with a Cauchy transform, and the Cauchy transform, of course, implements the moments of either the measure or the operator that you are interested in, and then you can actually recover the measure in this way. So this is also, or you can define a distribution by saying I have a Cauchy transform satisfying this or that property. This is how you could do
All right, thanks. These are some interesting phenomena. Okay, any questions? Okay, then thanks for sharing with us this exposition, and we'll be more ready for next week.
I hope so.
Thank you very much.
Thank you.
Okay. Good afternoon, everyone. So if anyone wants to have an informal chat, I'm scared of pressing the end for all button.
Max, I wanted to say something.
Yeah, sure.
When you asked about the...
Wait, I'm still recording. Maybe, do you want me to stop recording?
Oh, yeah. Well, I don't know. Maybe I was actually sorry I didn't say it, because maybe it could have been helpful for the students. But you see, if you want to know the moments, if you know the moments, for example, in the isomorphism problem, if you know all the moments generated by two tuples, then you know everything. So if you have two tuples generating the same moments, then they generate isomorphic for Neumann algebras.
Right.
Okay. So the goal is to know the moments.
So it's like some density of polynomials or something.
Wait. Now, because you asked about the Fourier transform. Now, even knowing the moments of the sum of two random variables is a challenge. Now, classically, if they're independent, then you can do it. If you know the distribution of x and y, the distribution of the sum is the convolution. And the Fourier transform, one of the great things is that it turns convolution into product. And you can analyze, you can analyze things. That's why the Fourier transform is the characteristic function of the measure, or of the of the RV. Now, it turns out that if two x and y are not independent, but freely independent, then the distribution of x plus y is not the convolution, it's something else. It's something else that behaves nicely with the Cauchy transform, behaves very nicely with the Cauchy, well, in a complicated way, but
True.
So that's why there you wanted Fourier transform, I think, and here you want a Cauchy transform. I think that kind of maybe explains it. Why here you have Fourier and here it's because you have a different kind of convolution for the sum.
Right. Yeah.
So I wonder that like I wasn't sure if it's right to ask it because maybe it's unrelated, but from the start of it, it sounds like this formalism of quantum mechanics, right? That you have a self-adjoint matrix, which the trace is the expectation, right? So like this classic example they have with momentum and position, does it fit some kind of independence or something like that? Or it's like a different story?
Not really. I mean, for instance, if you start with the or let me say it like this: you have these typical what's it called? I mean, the typical algebras by which you can somehow implement or which model these commutation relations that you're having in mind. And these are typical things are the creation and the annihilation operator on the full Fock space, or on a Q deformation of the Fock space. You can take the symmetric Fock space, or the anti-symmetric Fock space, or actually Q factors.
Right. So these are kind of examples that come up naturally.
Exactly, especially for the free for the full Fock space, which corresponds to the case Q equals 0. There it happens that that somehow the sum of left creation plus left annihilation operator for vectors being orthogonal, they happen to be freely independent. So this is what I meant when I said orthogonality gives you a free independence. It's really this orthogonality of the vectors for which you consider these sums of creation and annihilation operators, which then are freely independent with respect to the vacuum expectation. So what you do is you just take your operator, you apply to the vacuum vector, and then you take the inner product with the vacuum vector. And with respect to this state, you can really build up a non-commutative probability space. And it actually happened to be a tracial W star probability space, which is quite surprising because you wouldn't get a trace, of course, on all of B of H, but you get it this very particular way for Neumann algebra, and a very concrete trace on this for Neumann algebra. And in this for Neumann algebra, you see freeness coming out of orthogonality.
Okay. Okay, thanks. I can stop.